Hi, welcome back to my channel, and for today's video, we will be talking about the systems of linear equations by the aids of matrices, and in that way we can introduce the row reduced echelon form of a matrix to solve for the system of linear equation. For those who are new to my channel, please don't forget to click down there for you to subscribe. In that way, you'll be updated on a lot of videos that I'll be uploading soon. So for those who are new to my channel, please don't forget to click here to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. And for those who have been here for a very long time, thank you very much for your undying support. Okay, so let's start now. Given that you have systems of linear equation here, these are actually here coefficients on these variables, and these are actually also a constant. Now, these aij's here, same with your bi's, they're actually both coming from the same field. So it could be a real number, it could be a complex number. So depending on what the situation is. Okay, now if these bi's are actually 0, so assuming this b1 is 0 until b sub m, we call this system here as homogeneous system. Okay, that's it. So in this system of equations here, if you are going to count these aij's in one particular equation, there are actually n aij's here. And also, if you're going to count the number of equations, which corresponds to the number of bi's, there are actually m equations here, which means to say that there are n variables, so there are n unknowns with m equations. So this system is called systems of m and equations with n variables. That's it. So meaning to say that if you will be able to find an n tuple, let's say we have an n tuple, I'm gonna label that as C. So C1 up until Cn, which satisfies this system of equation, then we can say that this is actually a solution. So therefore, if you are asked to find the solution set of your system of equations, so I'm gonna correct that because I noticed a textbook in high school, I guess, that when the question was asked supposed to be find the solution set of the systems of equation, then the key answer would actually like this, like you have x equals 1, y equals 2, z equals 5, and so on like that. It shouldn't be that solution set because in the first place this is not written in a solution set. The solution set should be like this. Suppose for example that it's three tuples. So it's three tuples satisfying a certain system of equation wherein your x is 1, your y is 2, your z is 5. Then the solution set should be written like this: 1, 2, 5. In a manner that they are actually arranged from starting from x, then y, then goes to z. And that should be the solution set. It shouldn't be this answer written this way. That's not acceptable. That's it. Now, for a given system of equations, so you say, for example, you have a system S1, you have another system S2. We can only say that this S1 is equivalent to S2 if one of them, like either S1 or S2, can be obtained from the other via the following operations. So it could be either interchanging rows, it could be one is the multiple of the other, When I say one is the multiple of the other, This means that one equation coming from the other system is actually a multiple of one equation from the other system. And number three is adding a multiple of one equation, then added to the other equation. Okay, how I'm gonna show that? Let's say you have this system here. So I'm gonna show you an example here. So suppose that you have a system 3x plus 2y minus z equals, let's say 10. The other is 3x plus z equals 15. Okay. Let's say that's our system there. Now, we can have another system in which this system here is actually equivalent to this. If we have this way, let's say 6x plus 4y minus 2z equals 20, and then 3x plus z equals 15. So these two systems here, so let's say this is S1, this is S2, they are actually equivalent because if you notice, the first equation from S1 and the first equation in um, in S2 are actually related in the sense that the first equation in S2 is actually a multiple of the equation in S1. So if you're gonna multiply the first equation in S1 by 2, you simply get the equation in S2. So if you are given with an equation like 4x plus y equals 5, and then you have 3x minus 7 equals 0, let's assume that way, and then you have another equation 3x minus 5y equals 6, and then you have 3x minus y equals 4. So there's no way you can be able to say that these are actually equivalent because if you check the number one, there's no interchanging of rows happening. There's the other is not actually a multiple of the other, so you cannot have a relationship of this equation to the equations coming from the other system. And then even if you evaluate by adding a multiple of one equation to the other, you really can't find that way. So therefore, these systems here, this one and this one, are not equivalent, unlike with this previous example. So that's it. So if you are wondering why we need to know the equivalence of two systems, simply because two systems actually have the same solution. So if you will be, let's say for example, if system 1 has a solution of set of 1, 2, 3, then you are expecting that at system 2, provided that system 1 and system 2 are equivalent, then you should be expecting with the same solution set because they're actually equivalent to each other. That's it. Okay, so suppose for example, we are given with this system of equation here. So you have, let's say 4x minus 3y equals 6, and then x plus y equals 5. So suppose this is system 1 here. And then we have an equivalent system for system 1. We call this as system 2. And we have this 8x minus 6y equals 12. And then it could be 2x plus 2y equals 10. Okay, so they're actually equivalent because if you are going to evaluate that, these equations here are actually multiple of the equations coming from the first system. Now, if you're going to solve for the solution set here, so we're gonna solve that, and I'm gonna use the other color here to distinguish. So I would have, let's say, I'm gonna multiply this by 3 here, so I would have 4x minus 3y equals 6. I get 3x plus 3y equals 15. So I'd have 7x. And this will be 21, implying that my x is 3. And so my y is 2. So implying that the solution set is 3, 2. So this solution set here also actually satisfies this system because this S1 is equivalent to S2. That's it. Okay, so going back from our systems of equation, so as we have agreed earlier, these aij's here are actually coefficients. Then these are actually variables. So that means you have n variables coming from x1 to xn, and your bi's are actually constant here on the right side. So, in order for us to solve the systems of linear equations via the use of matrices, we can actually represent that in this way. Here, your A is a matrix, and this matrix is what we call a coefficient matrix, whose entries here are actually aij's. And then your X here is a column matrix. That means it's x1 up until xn. And then your B here is actually a column matrix. That's B1 to Bm. So for this coefficient matrix, these are actually entries of our coefficients from the systems of linear equations. So say for example, you have 3x plus 5y minus z plus w equals, let's say 11. You have 4x minus z plus w equals 7. And then you have 10x plus y minus w equals 2. And then you have 11x plus y minus z equals 10. Assuming these systems are actually does actually make sense. Well, anyway, the purpose here is to illustrate to you that to create a coefficient matrix for that, I would have 3, 5, minus 1, 1. So that corresponds to the coefficient here, assuming that the order is actually x, y, z, and w. Another is you have 4, 0, minus 1, 1. You have 10, 1, 0, minus 1. You have 11, 1, negative 1, 0. So this is actually your coefficient matrix now. That's it. Okay, so this time we are going to introduce to you the concept of the reduced row echelon form. The goal here is to find a row equivalent matrix to the coefficient matrix in which we can be able to easily get the solution of the systems of linear equation. Okay, so what is a row reduced echelon form or echelon matrix? So this is defined as a form if every zero row of R is at the bottom of the matrix. So that's number one fact. Number two, the first non-zero entry to the left in each non-zero row of R is equal to 1. So that's the leading one. And the leading one of a non-zero row I is to the left of the leading one of row I plus 1, if there is. And each column of R which contains a leading one has all its other entries 0. Okay, so to be able to picture out on that, I'm gonna show you an example here. This is an example of a row reduced echelon form. So you have 0, 0, 1, 0, 0. Okay, so that's an example of a reduced row echelon form or row reduced echelon matrix. So one common example also is that the identity matrix. So this one here, identity matrix of size 4, this is actually already a row reduced echelon form. That's it. Now, in the process of attaining a reduced row echelon form of a given matrix M by N of by size, now actually the reduced row echelon form of that given matrix is unique. However, the sequence of operation that we have done in order for us to achieve the reduced row echelon form is actually not. Okay, so one actually example in which we can be able to attain a certain matrix of size m by n to reduce row echelon form. In that way, we will be able to solve a systems of linear equation is the so-called Gauss-Jordan elimination method. Okay, so this is the Gauss-Jordan elimination method. I'm not going to simply tell you about the steps here, but I'm going to provide you an example in which we will use this Gauss-Jordan elimination method in order for us as to solve a system of linear equation. But first is let's start with just the basics system on with just the basic matrix only. So assuming I have I'm going to consider an example here. Okay, so let's consider an example here. So we are going to apply the process of Gauss-Jordan elimination method. And then our goal is to achieve the reduced row echelon form of the given matrix A. So in this case, the given matrix A here is you have entries 0, 0, 3, 0, 2, 2, negative 2, 3, 3, 3, negative 1, 4. So in order for us to achieve that, so let us recall the definition of the reduced row echelon form. So again, number one, every zero row of R is at the bottom of the matrix. And the first non-zero entry and the first non-zero entry to the left in each non-zero row of R is equal to 1, and the leading one of a non-zero R is to the left of the leading one of row I plus 1, if any, if there is. And number 4, each column of R which contains a leading one has all its other entries 0. So for us to do this, so if you notice, it starts with here with 2 zeros. Now, our goal here is that the 0 row of R should always be at the bottom. So we're not gonna start this with 0, 0. So I'm gonna swap R1 and R2 here. And so I would have a new matrix as 2, 2, negative 2, 3. I'd have 0, 0, 3, 0. I'd have 3, 3, negative 1, 4. Okay. Now, next goal that I'm gonna do here is I'm gonna simplify the first row. So I'd have R1, I'm gonna divide that by R by 2, and then that would be my new R1. So I'd have 1, 1, negative 1, 3 over 2. I'd have 0, 0, 3, 0, and then I have 3, 3, negative 1, 4. So a next thing that I'm gonna do with that is I'm gonna simplify the R3 here. And I want these first two here to be 0. So I'm gonna multiply negative 3 to R1 and I'm gonna add that to R3. So that will be my new R3. And then I'd have 1, 1, negative 1, 3, 2. This one here I'm gonna have 0, 0, 3, 0. And so finally I get here 0, 0, 2, negative 1 half. And then this is already the new matrix here, and my next goal here is also, by the way, I can reduce in this case here, I can reduce my R2. So I'm gonna divide that by 3 to get a new R2. So this is the one already here. And so my final is that my R2 will be added to R1. So I'd get 1, 1, 0, 3 over 2. And well, my R2 will still be the same. So that's 1, 0. And then the next thing I'm gonna do is I'm gonna simplify this. So I'm gonna have R1, it's negative no, it's negative R2. So I'm gonna have negative 2R2 plus R3, and that would be my new R3. So by multiplying negative 2 to the R2 here, and I'm gonna add that to R3, I would have 0, 0. And then this will be 0, so I'll get 0 here, and this is negative 1/2. Okay, so that's it. This is now my reduced row echelon form of a matrix A. Okay, so if you have any questions or clarifications, or if you might think that I may miss to give clarity on this process, you can comment down there so that I will be able to correct things out, and or I can provide you any further examples in relation to this problem. Okay, so let's consider another example here. We'd have this matrix here. So in order for us to achieve the reduced row echelon form for that, first is I'm gonna find the pivot on the first row, on the first column of the first row. So this is actually my leading one here. So everything here, my goal here, everything here is 0. So to do that, I would have to multiply negative 2 to R1, and I will add that to R2. That will be my new R2. So here, I'm gonna copy the one first, the first row. And then this will be 0, negative 1. This is 2, this is negative 2. So I'm gonna multiply negative 2R, it's negative 2 to R1, and then I add that to R2. That will be my new R2. Also, I'm gonna have to add here is the R3. So to make it 0, I'm gonna add this to R1. So I'm gonna have R1 plus R3. That will be my new R3. So I'd get 0, 0, 1, 2. Also, this is R4. So to make this 0, I'm gonna subtract that by R1. So I have negative R1 plus R4. And that will be my new R4. So that this becomes 0, negative 1, 1, 0. So in this case, we were able to achieve that this is the leading one here. This one here is the leading, so it's the pivot here. And then we will proceed with the next. So we will have to find the pivot on the row 2, column 2. So in this case, I'm gonna reverse the sign here. So this will be positive, this will be negative, this will be positive. So in this case, I have my new here as negative R2 plus R1, and that will be my new R1. So in this case, I'd have 1, 0, 2, negative 1. So my goal here is that this will be 0, this here will be 0, and this will be positive 1. So I'm just gonna copy 2 here because I did not do anything on 2 except that I do something on 2 to do the other rows, but I'm not gonna change the row 2 here. Okay, now to achieve the R3, oh, okay, we don't have to do something on R3. It's already 0, so I'm gonna just copy it as is. And then to achieve the R4, this is 1 here, and then this is negative 1. So I'm gonna add R2 to R4, and that will be my new R4. So I'd have 0, 0, and negative 1. Okay, that's negative 1, and then I'd have 2. Okay, now my next goal here is I'm gonna find a pivot on the third row and third column. So that means I'm gonna let this as 1 and the rest will be 0. Okay, so to do that, I'm gonna have negative 2R3. And I'm gonna add that to R1, and that will be my new R1. So I'd have 1, 0, this becomes 0, this becomes -5, and then for 2, so I'm gonna have 2R3 plus R2. That will be my new R2. And so I have 0, 1, 0, and that will be 6. I'm just gonna copy R3 because I did not do something on R3. It's except that I use the R3 to manipulate the other rows. And then I would have R3 will be added to R4 to get my new R4. So this is 0, 0, 0. And then by adding that, I would get this 4. So in this case, we already have achieved what the definition of reduced row echelon form. So this is now the final answer. So the reduced row echelon form of this given matrix. So assuming that this is a system of linear equation wherein these first three columns here are actually the coefficient matrix and these are actually BIs here, then we have achieved already the solution for the systems of linear equation. So in this case, supposing that our variables are x, y, and z, so our x here is -5, our y here is 6, and our z is 2. That's it. Okay, so that's all for now. Thank you so much for watching. So if you have any questions or clarifications about this video, you may comment down there so that we will know and we will be able to discuss. And that way, I will also know if I have made clarity on an emphasis on this concept and the example. In that way, I might be able to give you another video to support on this clarification for this concept. And thank you so much. And again, don't forget to subscribe to my channel for those who are new here so that you'll be updated on a lot of videos that I'll be uploading soon. Have a great day.